Alrighty, good morning everybody, and welcome back to Abstract Algebra. The plan for today is we're going to do something I do every semester. It's a little bit of course discussions, talking about what math courses are coming up in the spring and which ones I think you should take. Then we're going to prove this theorem, which we started talking about last time, but didn't get very far into, the converse of Lagrange's theorem for billion groups. And finally, we're going to jump into our next packet in a new chapter and talk about normal subgroups. Got my usual upstairs this afternoon at 2, tomorrow morning at 10, tomorrow afternoon at 1:30. And as a reminder, homework 5 is due tonight. So make sure you have that submitted to Blackboard. Any questions or comments before we get started today? Okay. So, 3 statisticians are out duck hunting one day. Duck flies overhead. First statistician shoots at the duck, misses. Shot 6 inches too high. Second statistician shoots at the duck and misses. 6 inches too low. Third statistician jumps up and down and says, "Yeah, we got it." Take the average. It was dead on. So, I like to just every semester just talk a little bit about what are kind of the since we're at the point in the semester where you've been given kind of the course schedules. Probably talk just a little bit about what are the math department's offerings for the spring. Have some idea of what I think are good follow-ups for this course. First of all, if you haven't taken Multivariable Calculus yet, you should take that. It's a fun course. Basically, Calc 3. Basically, if you haven't taken it, it's basically doing everything you did in Calc 1 except doing it in higher dimensions. So thinking about what does it mean to take derivatives in such of a 3D function? If you've ever been curious about that sort of thing, Multivariable Calculus is a good one. Plus, if you're taking this, you're probably like math a fair bit. And other than linear algebra, Multivariable Calculus is kind of the gateway course that's blocking off taking all the other courses that the department offers. Once you've taken multivariable and linear, you can take most of the courses within the department. This is a good one, if you haven't taken it yet. 330 is number theory. Which in some ways is like an easier version of this class. Basically, number theory is specifically the branch of math that looks at like properties of the integers. Things like how many prime numbers are there less than or equal to n? Looking at distribution of the prime numbers, properties of the integers. You do a lot of stuff with like modular arithmetic, like what we're doing in Z mod NZ. Number theory covers a lot of the same topics, but a little bit slower paced, a little bit of a more gentle course than this one, I would say. So something to consider. Feel free to stop me at any point. Ask questions. 340, differential equations. Oh, I forgot to mention. I'll mention how often each course is offered. Multivariable Calculus is every semester. You can take that whenever. There's 2 sections that are going to be offered this spring. Number theory is only once every 2 years. So if you want to take it, it's like next semester is likely your last opportunity. Differential equations is strangely once every 2 years, which is bizarre. I feel like it should be every year. That's a course that's sort of on the borderline between pure and applied math. You learn kind of a lot of like applied techniques for solving equations like y double prime minus y prime plus y equals 2, solve for y. And get into a lot of cool applications, and it's a really useful class. Only pure X linear, so all of you should be able to take it. It's only offered once every 2 years, especially if you're thinking about grad school or something like that. Differential equations is a good one. 380 is math modeling. Math modeling. By the way, multivariable calculus required for both pure and applied majors. Number theory is an elective. Differential equations is an elective. Math modeling is required for the applied major, but not for the pure math major. Doing math to solve a bunch of real-world problems. So if you're taking this class and you're fed up with nothing, and you're fed up with Dr. Gerstle just talking about abstract nonsense every day, math modeling, you'll probably do like get some experience programming, working on like projects, and like here's how you would use math if you were like a corporation trying to optimize things type stuff. Do a lot of that in math modeling. This one offered once a year every spring because it is required for the applied major. Real analysis. Oh boy. This one's offered every spring. This one is required for the pure major. You don't need to take it if you're taking the applied major because you're in this class. This is a lot like abstract algebra. It's going to be kind of a pretty challenging proof-based course. Basically going through and proving a lot of things that you kind of take for granted in calculus, like product rule, quotient rule. And I don't know. I haven't taught this before here, so I don't know what they teach. As someone who's taken the class. Lane, what do you do in that class?
Suffer.
Yeah.
Suffer.
It hurts. It hurts.
But it hurts less after taking abstract algebra, I think. I think typically whatever you take, and from what I've heard, whatever you take first of abstract algebra and real analysis is the harder, scarier one. So if you're taking this first, you will be ready for real analysis to kick off some proofs and to let epsilon be greater than 0. Topic scores. Real analysis, by the way, offered every spring. 415, we're offering a topics course in representation theory, which is this one's mine, so I'm excited about it. I'm teaching this one as a follow-up to, it's a follow-up to abstract algebra. And basically we're going to be looking at kind of a lot of connections between abstract algebra and linear algebra and graph theory. We're going to do things like, hey, check this out. It's a graph, right? Got a bunch of little points, got a bunch of lines, vertices, and edges connecting them. What we're going to be doing in that class is like, what if at each of these points you put a vector space? In other words, like a group with some other stuff attached to it. So put the complex numbers here, we'll put the integers here, we'll put the integers here, put the integers here, we'll put the complex numbers here, and because we're feeling rebellious, we'll put that there. And then for each edge, you be a homomorphism. So this is going to be a homomorphism from the complex numbers to the integers, from the integers to complex numbers, etc. And what sorts of wacky linear algebra results can you get out of doing this stuff? It's going to be a lot of fun. This one's mine, and you shouldn't take it unless you like this class. That is, it's not required for the major. This is just a 400 level elective, and this will be the only time that this is offered for a very long time. And the last one, 420. We'll laze it. Mathematical statistics. This is like the only one on the list you might not be eligible for because this one requires you've taken probability first. But if you've taken probability, this one's like a very like applied math course, like looking at kind of like advanced statistics, like the joke of the day today. This one's offered once every 2 years. And yeah, again, if you're interested in more kind of applied math, like you like math for its applications to the real world, then these are kind of more the courses you want to lean towards. Also this. Also that. If you're more interested in sort of abstract mathematics, math because math is cool and awesome and who cares about the real world type stuff, then you would be more interested in these. But what questions do you all got?
Are any of these 4 credits except, I think multivariable is?
This one, multivariable is a 4-credit class. The rest of these are 3 credits. And I guess there's a senior capstone. Which you have to take if you're a senior and you're not taking it right now. And that's a 1 credit.
Is that senior capstone in math?
That is in math, yes.
So if I'm like double majoring, do I have to take 2 capstones? Or?
You just need a single capstone.
Okay.
Yeah, I should specify. If you are a math major and or applied math major and you are a senior and you haven't taken another capstone, you should take this. You need to take it. Or a capstone in your other major if you have one in this room. Any other questions about any of these or my recommendations? Backup stuff? Okay. Capstone's every semester, but you need to take it this spring if you're going to. Ooh, yes.
I heard game theory is going to be offered next spring instead of this spring because of people like short staff, basically.
Yeah, game theory. That's a fun one.
Is that
Game theory is likely going to be offered sometime next year, maybe in the fall, maybe in the spring, maybe not at all. Definitely, almost certainly next summer, if nothing else. But that's a little bit up in the air right now.
Gotcha.
I'm not sure. If it gets offered, I'll be the one teaching it, and I would like to know when it's offered too. But that is the plan. Okay. Oh, in case you're curious, I'm doing Capstone, Hutchinson, me, Gabler, Bolasov, Trelaw, Webster, me. So, all right, let's do some math. If you have any more questions about any of these, I'm happy to talk to you more. Feel free to reach out to me in office hours. I'd be happy to give you recommendations based on what you've taken and what might be a good fit for you. Okay, so last time we had started talking about we had talked about our good old friend GAG, the fundamental theorem of finite abelian groups, which we use to answer the question of how can you classify all abelian groups of a fixed order. Basically, take the order, break it down into products of primes, and look at all the ways you can kind of separate out prime powers. And I'm going to use that to prove this following theorem for today, that if G is a finite abelian group and K divides the order of G, then G has to have a subgroup of order K. This is a result that we've already proven has to be true for cyclic groups. We've proven it doesn't have to be true for groups in general. Like the alternating group, for instance, gave a counterexample if we remove the word abelian. But if you have an abelian group, it turns out if K divides the order of your group, then you have to have a subgroup of order K. Here's our proof. So let's start by suppose G is finite abelian. And then we can use the fundamental theorem from last class to say that G has to be isomorphic to something of the form Z mod P1 to the alpha 1 plus Z mod P2 to the alpha 2, blah, 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 Z mod P sub n to the alpha n for some primes P sub I and some alpha sub I satisfying the order of G is equal to P1 to the alpha 1, P2 to the alpha 2, up through Pn to the alpha sub n. So in other words, suppose we have a finite abelian group, and then the fundamental theorem of finite abelian groups tells us something. It tells us then that our group has to be isomorphic to something of this form, where if we multiply all these prime powers, we get the order of the group. That's what the fundamental theorem tells us has to happen. So then, if K divides the order of G, i.e., if K divides the expression P1 to the alpha 1, P2 to the alpha 2, up through Pn to the alpha n, what can we say about K? So we're assuming that we have some number K, some positive integer, that divides the product of all these P's. P1 to the alpha 1 times P2 to the alpha 2, etc., etc. What can we say about K? In particular, what can we say about the prime factorization of K if K divides this product of primes? What does the prime factorization of K have to look like? We had talked a little about this right at the end of class last time. What?
It has to be like P1 to the Q1, P2 to the Q2, dot, 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 Pn to Qn for some Q of whatever less than or equal to R.
So in other words, K has to have the exact same prime factors as the order of G, but just fewer of them. The only way for K to divide the order of G is if K has all the same prime factors except less. In other words, K can't have any prime factors that the order of G does not. So you say then K is equal to P1 to the R sub 1 times P2 to the R sub 2 up through Pn to the R sub n for some R sub I less than or equal to the alpha sub I. So K is going to have the same prime factors, the same prime powers, but just fewer of them. Where R sub I potentially could just be 0 if we don't include, say, P sub 1 at all. If we don't include P sub 1 at all, then we would just say, and then just include P sub 1 to the 0th power. So we know something about K. It's equal to P1 R1, P2 R2, blah, blah, blah. Then, for each P sub I claim P sub I has to, P sub I to the R sub I has to divide P sub I to the alpha sub I. Since each R sub I is less than or equal to alpha sub I. So in other words, if we just look at the individual prime powers now, since each R is less than the corresponding alpha, P to the R is going to divide P to the corresponding alpha. Because it's like, if I have 3 factors of 2, 2 to the 2 cubed is going to divide 2 to the 5th. I just have to take 2 cubed multiplied by 2 more factors of 2 to get up to 2 to the 5th. So each P sub I is going to, P sub I to the R sub I is going to divide each corresponding P sub I to the alpha sub I. Well then, hold on to your hats. Now we're going to use a different theorem. We're going to use the fundamental theorem of cyclic groups. So then by the fundamental theorem of cyclic groups, the one that says every cyclic group has exactly one subgroup of each order dividing the order of the group. Each z mod P sub I to the alpha sub I must have a subgroup H sub I of order P sub I to the R sub I. So in other words, we know each one of these cyclic terms, z mod P sub I to the alpha sub I, we know those are all going to be cyclic groups. And since we know that cyclic groups have to have subgroups of each order dividing the order of the group, since P sub I to the R sub I divides the order of each one of these cyclic groups, this term here divides the order of each one of these cyclic groups, we know each one of those cyclic groups has to have a subgroup of this order. In fact, it has to have exactly one subgroup of this order, according to the fundamental theorem, but we just need that there's at least one. And for each of these, the subgroup of order P sub I to the R sub I that is guaranteed, I'm just going to call H sub I in each case. Just a subgroup of Z mod P sub I to the alpha, P sub I to the alpha sub I, and the order is P sub I to the R sub I. I'm saying the word sub I a lot, but it's just fun to say. I'm going to stop here and just pause for a second and see what questions you all have. Our goal, keep in mind, is to show that G has to have a subgroup of this order. And we're about to construct what that subgroup is. Keeping in mind, we found each one of these terms, we found a subgroup for every single one of these individual groups. We found a subgroup of this one of order P sub 1 to the R sub 1. We found a subgroup of this, H2, of order P sub 2 to the R sub 2. etc., etc. We found subgroups of each one of these things. And then it turns out to get our subgroup that we're looking for, we just have to take the direct product of all the h's. So in other words, then h, which we're going to define to be equal to h1 direct product h2 up through h sub n, what do we know about this? This is going to be a subgroup of it's a subgroup of z mod p1 to the alpha 1, direct product z mod p2 to the alpha 2, up to z mod p sub n to the alpha sub n. And this is technically using a property we haven't proven, that if h1 is a subgroup of this thing, h2 is a subgroup of this thing, etc., etc., if all of these h's are subgroups of these things, then the direct product of the h's is going to be a subgroup of the direct products of the z mod nz's. I hope you can believe that. But this thing is isomorphic to G, and here's the kicker. If H1 has order P1 to the R1, H2 has P2 to the R2, blah, 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 Hn has order P sub n to the R sub n, what's going to be the order of this H if we take the direct products of all these H sub i's? Right?
Is it K?
It is indeed. By definition, the order of H is just going to be the order of H1 times the order of H2 times up through the order of Hn. The order of the direct product is just you multiply the orders of each of the component groups. But H1, order of H1, we said is just P1 to the R sub 1. Order of H2 is P sub 2 to the R sub 2. Order of H sub n is P sub n to the R sub n. And if we multiply these all together, we get K. And then finish things off, we can say, since, I'm going to give this thing a name. I'm going to call this A. And I'm going to say, since this direct product of all the Z mod P things, since A is isomorphic to G, and A has a subgroup of order P, or of order K, G must also have a subgroup of order K. Basically saying, since this thing, which I'm calling A, and our original G are isomorphic to each other, we've shown that A has a subgroup of order K. Part of the property of, what it means for two groups to be isomorphic is if one group has a subgroup of order K, then the other also has to have a subgroup of order K. And if you don't believe, if you don't believe me, that's okay. I'll make you prove it on the next exam. So what we just showed is that the converse to Lagrange's theorem, this thing we said doesn't work for the alternating group, A5 for instance, the thing that doesn't necessarily hold for groups in general does have to hold for abelian groups. If K divides the order of an abelian group, then the abelian group has to have a subgroup of order K.
Can you just explain why K has to include all of the prime numbers that were in?
It doesn't. It doesn't. And that's why I allow for the R sub i's could potentially be 0.
Then how does that work with when we say P divided R sub I divides the I alpha to the I?
Well,
What if that's 0?
let's look at a quick example. Let's say 4 times 9, 36. Let's say our K is 36, which is going to be what, 4 squared? No, 2 squared times 3 squared. I claim that, let's say not K, let's say the order of our group is 36. 2 squared times 3 squared. We could let our K, for instance, be just 9, which is 3 squared. That's 9 something that divides 36, right? We could just write this as 2 to the 0 times 3 squared, because 2 to the 0 is just 1. Multiplying by it doesn't change anything. And then you could still say, in this case, we would just have that our alpha 1 is 2, our alpha 2 is 2, our r sub 2 would be 2, our r sub 1 would be 0 in this case. And we would still have that k divides the order of g, even though we kind of don't have any prime factors of 2 at all. In that case, we would just say, just let that r sub corresponding r sub I be 0, and then you just get p1 to the 0th power, which just doesn't affect anything at all. Does that make sense? Yeah, good question. Any other questions before we look at an example of something? All right. So if you remember, we have this nice property of cyclic, this fundamental theorem of cyclic groups that says if your group is cyclic, then you can only have a single subgroup of each order dividing the order of the group. So if you recall, we said if G is cyclic and K divides the order of G, then G can only have one subgroup of order K. That's part of the fundamental theorem of cyclic groups, the thing we proved way back in chapter 4, I believe. We've just shown that a finite abelian group has to have at least one subgroup of order K, or just abelian in general, by a show of thumbs. Thumbs up for if you believe me, thumbs down if you don't believe me. Would you believe me if I told you that a finite abelian group can only have one subgroup of order K? Why are you voting? Why don't you believe me?
I think you recall you saying something about it last time this came up, but I don't remember what.
Fair enough. Turns out this doesn't have to hold true for abelian groups. You can have an abelian group that has multiple subgroups of the same order. Here's an example. This is not true for abelian groups in general. Check this out. I want my group G be the group Z mod 8Z direct product Z mod 8Z. I claim I can find two subgroups of order 4. So here's one of them. If we just take the subgroup of Z mod 8 that's generated by 4, so this would just literally include 0 and 4 as a subgroup of Z mod 8Z. If we just take that subgroup, direct product itself, that's going to be a subgroup of G that has order 4. You think of another subgroup of Z mod 8 plus Z mod 8 that has order 4. I claim you can find another one by picking our generators a little bit different. What would be two different elements that of Z mod 8Z that if we took the direct product of the groups they generated would give us a subgroup of order 4 other than 4 and 4? You know what? What?
0 and 2?
Ooh, 0 and 2. This is going to give us 0 elements. This is going to give us 4 elements. That'll work. Or technically, sorry, not 0 elements, 1 element, namely just 0 itself. This is going to give us 4 elements, 0, 2, 4, and 6. Yeah, that'll do it. Here, have a bonus. Boom, third subgroup of order 4. It's going to turn out that these last two are both going to be isomorphic to Z mod 4. This first one is going to be isomorphic to Z2, direct product Z2. So it is totally possible for an abelian group to have multiple subgroups that are all of the same order. It's not possible for cyclic groups, but this G happens to be an abelian group that is not itself cyclic, because 8 is not relatively prime to itself. And so here we have an example of an abelian group that has multiple subgroups of the same order. I know, Dr. Keitel, it's hilarious. Questions or comments? All right, next packet. So last packet was on direct products, which is our way of multiplying 2 or more groups to give a single supergroup, a big group. This packet, we're going to be building towards a definition of what it means to take a group divided by one of its subgroups. And we're going to get something called a quotient group when we do that. But we won't get to that. We won't actually get to quotient groups today. We've got some definitions to build up first. First of all, we need to know about something called a normal subgroup. This one. So in general, we're going to say that if H is a subgroup of G, we're going to say that H is a normal subgroup of G. Normal subgroup of G, which we denote with this funky symbol, H, and then a little triangle equal, not less than or equal to, but like a little triangle or equal to G. If for all elements G in the group, GH equals HG. So in other words, a subgroup H is a normal subgroup of G if all of the left cosets of H are exactly the same as all of the right cosets of H. If whenever you take H and multiply on the left by G, you always get the same thing as if you take H and multiply on the right by G. And if this checks out, we say the subgroup is normal. So let's look at a couple examples. So something to keep in mind, if we want to have a normal subgroup, it has to be the case that the left and right coset, when we're multiplying the left and right by G, gives you the same coset, the same set of elements, for every element little g in your group. So if you want to prove something is a normal subgroup, you have to show that every left coset is equal to the equivalent right coset. So to prove something is not a normal subgroup, you just need to find a single left coset and a single right coset that are not equal to each other. Any guesses offhand if my first example is going to be an example or a counterexample? I didn't.
Maybe a counterexample?
Correct. Turns out this is not a normal subgroup, so let's prove it. It's actually I'm not going to say pretty, it's relatively easy to prove something is not a normal subgroup. You just find some element in your group, in this case an S4, such that if you take the left coset of this subgroup, by that element, you get something different than the right one. And it's going to turn out to be the case that if we take the 2 cycle, 1, 3, and multiply on the left by h, we're going to get something different than if we take h and multiply on the right by 1, 3. So let's see what happens. So if we want to take 1, 3 times h, keeping in mind here that h is just going to have the identity element in it and the 2 cycle, 1, 2. If we take everything in h and multiply on the left by 1, 3, we're going to get 1, 3 times the identity and 1, 3 times the 2 cycle, 1, 2. Which if we multiply out, I'll do the hard one. 1, 3 times the identity is just 1, 3. What are we going to get if we take 1, 3 and multiply in S4 by the 2 cycle 1, 2? Right?
1, 2, 3.
1 is going to map to 2. 2 maps to itself, so 1 will map to 2 as we work our way from right to left. 2 maps to 1. 1 maps to 3, so overall 2 is going to map to 3. 3 maps to itself. 3 maps to 1. I agree. So the left coset of h that we get when we multiply everything in h on the left by 1, 3 is going to have 1, 3 itself and 1, 2, 3. Whereas if we try and repeat the same process, but on the right, meaning we take the identity times 1, 3 and 1, 2 times 1, 3, this time things are going to go less rosy. We're still going to get 1, 3, but now 1's going to map to 3, which maps to itself. 1 maps to 3. 3 maps to 1, which maps to 2. 2 maps to itself, which maps to 1. Are these the same set of elements? No way, Jose. And we could say that since 1, 3 times h is not equal to h times 1, 3, h is not a normal subgroup. Because it has a left coset and a right coset that are not equal to each other. And since this doesn't work out for a single coset, it's not a normal subgroup. Because in order to be normal, this would have to work out for all possible cosets of h on the left and right. Any questions about this example? Let's do an actual example of one now. Turns out that if we take the subgroup generated by R in D3, I claim that is going to give us a normal subgroup. So our left coset, or let's write down an example. So in this case, I'm going to let h be equal to the subgroup just generated by R. So the identity R and R squared. I'm going to ask the question, is that a normal subgroup of D3? Spoiler alert, yes. How many cosets does H have in D3? Hint, Lagrange's theorem. If H has 3 elements, and D3, the whole group, has 6 elements, how many cosets is H going to have? Or unique cosets? Right? 2, because 3 times 2 is 6. Remember, the number of cosets a subgroup has is always going to be the order of the whole group, in this case 6, divided by the order of the subgroup, in this case 3. So we're going to have 2 left cosets and 2 right cosets. One's just going to be the identity times h. The other we can represent by just taking s times h. And so our right cosets, one's going to be h times e. The other is going to be h times s. And so to check, is H a normal subgroup of D3, we need to check, does EH equal HE? Are these left and right cosets the same? I mean, those are just going to be H, so these are equal. And we also need to check, does SH give us the same thing as HS? Because if so, we would have a normal subgroup. So EH equals HE, because if you just multiply everything on the left or the right by the identity element, nothing changes. So this left coset and this right coset are be the same. They're just both going to be the same thing as H. We also need to check, does SH equal HS? So if we take everything in H and multiply on the left by S, we're going to get S times E, S times R squared, which we do a little multiplication. S times the identity is just S. Which element of D3 are we going to get if we take S times R? Wayne?
Is it R squared S?
It is indeed. You hate that what?
I hate that I have that memorized now.
Be happy that you have that memorized. Now you can use that as an example and be ready to do whatever you want in class all the time. Never hate having knowledge, unless it's sad knowledge, which is. And similarly, SR squared is just going to be RS. On the other hand, we take H times S. We're going to get same thing, except now we're multiplying everything in H on the right by S. So we'll get RS and R squared S, which the only thing we need to multiply is E times S is S here. And now, are these the same set? See some nods? They are indeed. They have the exact same elements, an S, an RS, and an R squared S. Even though they're written in a slightly different order, these are still the same. Equals. So what we just showed is that for all elements G and D3, G times H is equal to H times G. Hence, in this case, H is going to be a normal subgroup of G. Because all the left cosets equal all the corresponding right cosets. Whereas over here, it only took a single counterexample, a single left and right coset that didn't match up in order to show that this is not a normal subgroup. It turns out that if this one checked out and that every left coset matched up with all of the corresponding right cosets, we only had two pairs to check. And so this one did give us all. Questions, comments, concerns? As far as you know, yes. In the next packet, we're actually gonna see kind of a much slicker way of checking if something's normal, it's gonna. Do you want it to scroll down?
No.
There's a cool way to actually check that involves group homomorphisms. I will say. I'll just tell you that much. But yeah, now there is typically, in general, you don't go through and check if something's a normal subgroup by checking every single coset, because if there's only two pairs to check, then sure, that's not so bad. What if we look at a group that has 100 cosets, or a subgroup that has 100 cosets, like in Z mod 200Z or something? Then our lives are set. Also, something I want to note is something that's kind of cool. Is we just showed that if we take S times the group generated by R, we get the same thing as group generated by R times S. despite the fact that SR itself does not equal RS. On an element level, SR and RS are not the same. SR, remember, is R squared S. But if we take S times the group generated by R, we take the coset, this group multiplied everything on the left by S, we still will get the same coset as if we take the same elements as if we take everything in this group and multiply on the right by S. Simply because SR and SR squared give us the same thing as RS and R squared S, just in the opposite order. SR is equal to R squared S, SR squared is equal to RS. And I think that's pretty cool. It's a little surprising, kind of cool. I'm a fan. Actually, on the next page, I forgot, there's a theorem on the second page that gives you another way of checking if something's normal. The theorem on the second page is not any easier to check for the record, but it's going to give us a nice lemma on a way of proving a cool result. So, it's a fun theorem for you. Here's one way you could check. If H is a subgroup of G, then H is a normal subgroup of G, meaning all the left and right cosets check out, if and only if little g H, little g inverse is a subset of H for all elements G in G. So you may remember, Dr. Gerstle, what the heck is this? You just multiplied H on the left by and on the right by something. You may recall this is something that showed up in homework number 2. Like problem 6 on homework 2 involved like if H is cyclic, this is cyclic. If H is a subgroup, this is a subgroup. If H is abelian, this thing's abelian. We define this explicitly to be the set of all elements of this form, where the set of all things that can be written in the form little g times something in H times little g inverse. And it turns out if all of these elements, if all products of this form end up giving you elements in H, that's logically equivalent to saying H is a normal subgroup of G. That'd be it. We'll prove this result at the start of class on Friday. And then once we prove this result, we'll talk about why do we care about normal subgroups at all. It's going to be because normal subgroups are the things we're allowed to divide by in order to get quotient groups. I know, Elaine, it's crazy. See y'all on Friday.